In this video, we're going to talk about how J.J. Thomson discovered the electron in 1897 using the cathode ray tube experiment. So these days, we think about atoms kind of like this. They're made up of a variety of smaller subatomic particles. But in the late 1800s, it was all about John Dalton's model of the atom. In the early 1800s, John Dalton had proposed that all matter, all stuff, was made up of tiny, indivisible particles called atoms. At first, not many people believed him. But throughout the course of the 1800s, more and more scientists got on board with his idea. But it remained an open question whether the atoms were really indivisible. Were they like tiny little billiard balls, hard and solid? Or were they made of smaller things? No one really knew the answer to that. But J.J. Thomson was able to answer part of that question when he discovered the electron. He discovered that it was much smaller than atoms. He discovered that atoms had electrons. And so he was able to say for the first time that atoms weren't totally solid and indivisible, but they were made up of smaller, subatomic particles. Let's look at how he discovered the electron. So Thomson used what's called a cathode ray tube. It's a big tube of glass that's kind of like a bottle. You can imagine it sort of like this soda bottle. It's sealed all over, and then you pump all the air out of it. Okay? And it has these two pieces of metal at this end. So Thomson connected these two pieces of metal to a power source, and here's what happened. A ray shot from this piece of metal across the tube and created a glowing spot over here when it hit a special coating on the inside of the glass. Now, Thomson didn't know what was going on, but what really was going on is that electrons from this piece of metal were shooting out. They were attracted to this piece of metal, which has an opposite charge, but they were moving so fast that they shot all the way across the length of the tube. Anyway, Thomson sees this ray, and he gets curious as to what it's made of. And so he asks the question, the stuff that the cathode ray is made of, does it have an electrical charge? And here's how he attempts to answer that question. He takes two metal plates and puts them on either side of the cathode ray tube. And then he turns on electricity, which makes the top plate positively charged and the bottom plate negatively charged. And check out what happens to the cathode ray. When he turns on the power, he sees that now instead of going straight through, the cathode ray bends up. It bends up towards the positively charged plate. So based on this, he reasons that the cathode ray must be made of stuff that's negatively charged, since it's attracted to the positively charged piece of metal, and he knows that opposite charges attract. But just because he wants to be very careful, he's a very careful guy, he tries to check this another way. So he uses a magnet. If something has an electrical charge and it's moving, a magnet will push it in particular directions. So he takes a cathode ray tube, if you want to think that this marker is kind of the cathode ray tube, and he surrounds it with a magnet, just like this. We can kind of show what goes on by slipping the magnet under like this. So anyway, he puts the magnet here, and he sees now that the cathode ray bends in the other direction. It now moves downward. Now, if the cathode ray is indeed negatively charged, this is exactly how he would expect it to move in the presence of a magnet like this. So this is just further confirmation that whatever makes up the cathode ray probably is negatively charged. So he takes the data that he gets from these experiments, and he's able to draw a few important conclusions about cathode rays and what makes up atoms. Okay, so based on the outcomes of the experiments with the charged plates and the magnet, Thomson is able to conclude that cathode rays must be made of stuff that is negatively charged. Okay. He combines the information that he got from the experiments that I just told you about with some other data that he collected. And he's able to come to the conclusion that the particles that make up cathode rays are 1,000 times smaller than a hydrogen atom. Hydrogen atoms are the smallest atoms. So this thing that's in the cathode rays must be really, really tiny compared to an atom. And finally, Thomson swaps out the type of metal that's in the cathode tube. He uses a variety of different types of metal, but he finds that all of the different metals he uses give off the same cathode rays, and regardless of what metal he uses, the size of the things that are in the cathode rays is exactly the same. So based on these three conclusions, he's able to come up with the idea that atoms have tiny, negatively charged particles inside them, and these things that we're talking about here are electrons. Now, if you're like me when I first learned this, you might be confused how these conclusions definitely tell him that there are electrons inside atoms. I remember when I first learned this stuff, I was thinking like, wait, doesn't this just show that electricity or cathode rays have negatively charged stuff? How does this tell us anything about the atoms? Okay, here's why. At the time that Thomson does his experiment, everyone, for the most part, agrees that all things are made up of atoms, that atoms are the smallest things that make everything up. They're like the smallest things in the universe. So if Thomson is able to show that there are even tinier things, well, where are those tiny things coming from? They have to be coming from atoms because everything's made of atoms, right? That's the only place they can be coming from. And even if electricity, even if you want to say that, oh, well, he's just showing that electricity is made of electrons, well, then still, where are the electrons coming from that make the electricity? The electrons have to be coming from other atoms. And since he can move or remove these pieces of metal and swap other metals in, and he still gets electrons, it again shows that all different types of atoms are able to release or give off electrons. So they must be in there to begin with. Anyway, these conclusions that Thomson comes to have dramatic effects on how scientists think about what the atom actually looks like. Now, at the beginning of the video, we said that in Dalton's atomic model, atoms are indivisible, that they're not made of anything smaller. But when Thomson discovered that atoms have tiny negatively charged electrons inside them, he essentially disproved this model, at least the part about the indivisible atoms. So here is the model of the atom that Thomson comes up with. He realizes, first of all, that electrons are negative. We already talked about that. But then he notices that on the whole, atoms in general are usually electrically neutral. So even though they have these negatively charged electrons inside them, the atoms as a whole don't have a charge. So Thomson realizes that in order for the atoms not to have a charge, there must be some positive charge in the atom that can balance out the negative charge of the electrons. And then the positive and the negative balance out, and the atom then as a whole doesn't have a charge. So he comes up with a model that he calls the plum pudding atom. Now, plum pudding is kind of a British thing, so if you're American, it might be better for you to think about this as like the blueberry muffin model. And here's how it works. Thomson imagines that the atom is like a blueberry muffin, and that electrons are stuck in this atom the way blueberries are stuck in a blueberry muffin. So you have these little electrons that are stuck in the atom, but then they're surrounded sort of by a dough. And the dough, like in a blueberry muffin, keeps these electrons or blueberries held in place, but the dough itself has a positive charge. And it's that positively charged dough that is what balances out the negative charge of the electrons, and so together they don't have any total net charge. So the atom is electrically neutral. So that's how J.J. Thomson's discovery of the electrons leads to this plum pudding model of the atom. But now J.J. Thomson didn't have it quite right, because it turns out that the positive charge in the atom isn't sort of spread out in this dough or pudding, but instead it's concentrated right in the center of the atom where the nucleus is. So that's going to be the next step in discovering what the atom really looks like. If you're interested in how scientists disproved J.J. Thomson's plum pudding model, check out Rutherford's gold foil experiment, where he discovers that atoms have a very small, very dense, positively charged nucleus.